Hello, everyone. Today, we're going to cover Chapter 12, Part B. In this part, we'll talk about inventory management models. In inventory management models, we have two key questions: how much inventory to buy and when to buy. So we have several inventory models, and we can classify them as follows. Some models can handle variable demand, and others can handle stable demand. In other words, constant demand. So what's the difference between the two? Let's take an example. Suppose the daily demand of product A was 10, 10, 10, 10. So the first day, the demand was 10. The second day, the demand was 10, etc. In the past 12 days, the daily demand of product A is stable or constant. It doesn't change from one day to another. That's what we mean by constant demand or stable demand. Now, on the other hand, suppose the daily demand of product B was 16. On the first day, it was 16. The second day, the demand was 12. The following day, 6, 9, etc. in the past 12 days. So if you average these numbers, you get 10 per day. So the average demand is the same as before, but the actual daily demand varies from one day to another. So demand is variable. It fluctuates over time. So now we can classify inventory models according to whether demand is variable or stable. And we can also classify them according to whether we need short-term planning or long-term planning. So when do we need short-term planning and when do we need long-term planning? We need short-term planning when we have perishable products. Perishable products are the ones with very short shelf life. For example, if you're producing swimming suits, they need to be sold over the summer. If there is any leftover, you need to mark them down and sell them next year. And to prevent the markdown, we need to sell them out over the summer. On the other hand, you need long-term planning if you have products with very long shelf life. For example, if you're producing detergent, you can sell your product anytime in the next few years. So let's take some examples. Newspapers. Does it have a long shelf life or a short shelf life? Can you sell today's newspaper tomorrow? No. So this has a very short shelf life. Swimming suits, does it have a long shelf life or short shelf life? Short shelf life. Wooden tables, long shelf life. Plastic cups, long shelf life. So let's look at this table. Let's look at the lower right corner. This is a case where demand is stable and we have a short shelf life. So for example, we are producing swimming suits for the upcoming summer and demand is constant. That means we know exactly how much demand we're going to have. For example, we know exactly 100 customers will want to buy our swimming suits. Then, how many swimming suits should we produce for the upcoming summer? This is a trivial question. We just need to produce 100 swimming suits. Trivial. Let's go to this case. This is a case where you have a variable demand and products with very short shelf life. We have a model called the Newsbender model, and this is also called the Newsboy model. Now let's look at this case. This is a case where demand is variable and we have a long shelf life. And we can use a model called quantity reorder point model or QR model. Now let's look at the case. This is the case where demand is constant and we have long shelf life products. We have a model called economic order quantity model, and this is called the EOQ model. And for the rest of this chapter, we're going to talk about the EOQ model. So let's take an example. Suppose you are a retailer who imports Colombia coffee from South America and sells it to local customers. Demand has been constant at the rate of 1,000 pounds a year. The unit cost is $2 per pound, and the ordering cost amounts to $100 each time you place an order. The holding costs are based on a 40% annual rate. How many pounds of coffee should you order whenever you place an order to minimize the total annual cost? So in this question, we need to determine how many pounds of coffee we need to order. We need to determine the order size, the order quantity, and we need to minimize the total annual cost. So let's think about what we should include in the total cost. First of all, we need to pay for the coffee. We pay $2 per pound. So the price we pay for the coffee is called the purchase cost. What else is there? Each time you place an order, there's a fixed cost. It's called the ordering cost. And this includes the shipping charges and the order processing cost. And it's $100 a year per order. And what else is there? There is the inventory holding cost. How much is the inventory holding cost? The holding costs are based on a 40% annual interest rate. So the inventory holding cost per unit per year is 40% of the unit cost, right? To purchase 1 pound of coffee, you need to pay $2. So that's how much you invest to purchase 1 unit. And 40% of that, that's 80 cents per pound per year. And the annual demand is 1,000 pounds. And we will denote the unit cost by U, the ordering cost by O, and the inventory holding cost per unit per year by H, and the annual demand by D. Now, first, let's look at the following 4 scenarios, and we'll compute the total annual cost for each of these scenarios. In the first scenario, we're going to order only once a year. So the number of orders per year, N equals 1. At the beginning of each year, we place an order. In the second scenario, we place 2 orders a year. At the beginning of each year, you place an order, and 6 months later, we place another order. In the next scenario, we place 4 orders a year, and next we place 8 orders a year. So in this table, we're going to focus on these 4 scenarios, and we're going to compute the total annual cost. So let's fill out this table. Let's compute the order quantity, the ordering cost per year, the purchase cost per year, and the inventory holding cost per year. So let's start with the order quantity. When we place 1 order every year at the beginning of each year, how many pounds of coffee should you order? Remember, the annual demand is 1,000 pounds. That means throughout the year, we're going to sell 1,000 pounds of coffee. And since we only place an order once a year, you need to order 1,000 pounds. Next, if you place 2 orders a year, how many pounds of coffee should you order every time you place an order? Again, throughout the year, we're going to need 1,000 pounds, and we need to split this into 2 orders. So each order should have a half of 1,000 pounds, which is 500 pounds. So 1,000, you'd split it into 2, 500. Next, if you place 4 orders a year, how many pounds of coffee should you order each time you place an order? You need 1,000 pounds throughout the year. You split this into 4 orders, so you need 250 pounds per order. Next, 8 orders a year, so it's going to be 125 pounds per order. Now, can you find the formula for the order quantity, Q? So when we compute the order quantity, we took 1,000, which was the annual demand, and we divided it into N. Okay. Now, can we express this in terms of, can we express N in terms of Q? Yes, right? If you multiply each side by N times N, you get Q times N equals D. And if you divide each side by Q, you'll get N equals D over Q. Okay? Now, let's compute the ordering cost per year. Now, the first case, when you place 1 order every year, what's the ordering cost? The ordering cost is $100 per year. So since we ordered once, it's 1 times 100, which is 100. Next case, if you order twice a year, the ordering cost is 2 times 100, which is 200. Next, 4 times a year times 100, 400. Next, 8 times a year, 800. Now, can you find the formula for the ordering cost? Yes, the ordering cost was per year is this, the number of orders per year, N, times 100, which was the ordering cost, O. Now, remember, we have an expression for N. N was D over Q. So can we replace N with D over Q? Yes, right? So this is the formula for the ordering cost per year. Now let's compute the purchase cost per year. So if you order once a year, how much is the purchase cost per year? In this order, we are ordering 1,000 pounds. And for each pound, you need to pay $2. So it's $2,000 for the coffee. Next, if you order twice a year, and each order includes 500 pounds of coffee, and since we placed 2 orders, it's going to be 1,000 pounds again. 2,000. Next, 4 orders a year. And in each order, you have 250 pounds of coffee. So the total is 1,000 pounds of coffee and $2 each. That's 2,000. And finally, again, you purchase 1,000 pounds of coffee a year. So the purchase cost is 2,000. Can you find the formula for the annual purchase cost? Purchase cost. So you can realize that regardless of how many orders you place a year, you always take 1,000 pounds, which is the annual demand, and you multiply by 2, which is the unit cost. So the annual purchase cost is D times U. Next, let's compute the inventory holding cost per year. So if you place 1 order every year, how much is the inventory holding cost per year? We know the inventory holding cost per unit per year. That's 80 cents per pound per year. But in your inventory, you have more than one unit. So we need to take 80 cents and multiply by the number of units you're holding in inventory. So here is a question. How many units are we holding in inventory? At the beginning of a year, you have 1,000 pounds in inventory, but throughout the year, you will keep selling your inventory, and at the end of the year, you run out. So you have 0 units in inventory. Your inventory level will change over time. So what inventory level should you use when we are computing the inventory holding cost per year? So let's look at this graph. Let's see how the inventory level changes over time. The x-axis is the time, the y-axis is the inventory level. This is year 1, this is year 2. Let's just focus on year 1. At the beginning of year 1, you order 1,000 pounds. And then throughout the year, you sell this inventory. At the end of the year, you run out. And this is repeated over and over again, right? So at the beginning of the year, you have 1,000 pounds. At the end of the year, you have 0 pounds. Should you take 80 cents and multiply by 1,000? Or should you take 80 cents and multiply by 0? How about if we meet halfway, right? How about if we compute the average level, which is average of 1,000 and 0, 500, and then multiply 80 cents by 500. And that's going to be the annual inventory holding cost. So it's going to be $400 a year. Now let's look at the second case. Here, can you find the formula for the annual inventory level, average inventory level? That's the inventory level averaged over time, and in practice, you compute this level as follows. Sum of the daily inventory levels, right? And divide it by the number of days, or in this case, we just take something in the middle. The order quantity plus 0, the order quantity plus 0 divided by 2, that's Q over 2. Now, let's look at the second scenario where you place 2 orders every year. So this is how your inventory level changes over time. This is the first year. At the beginning of the first year, you place you order 500 pounds, and 6 months later, you run out and you order another 500 pounds. So in this case, how much is the inventory holding cost? We know it's 80 cents per unit, but how many units are we holding in inventory on average? Since your inventory level is changing continuously between 500 and 0, your average inventory is the average of 500 and 0, which is 250. So you take 80 cents and multiply by 250, so you get $200 per year. So this was 400, 200. So can you find the formula for the inventory holding cost? Yes, we took the average inventory level, which is Q over 2, and you multiplied by H, which is 80 cents per pound. Right? So using this formula, we can compute the inventory holding cost. And let's find the total cost per year. That's the sum. We have 3 types of costs: ordering cost, purchase cost, and the inventory holding cost. So the total annual cost is the sum of these costs. So add these up, you get 2,500. And Also, add this up, you get 2,400. Add this up, you get 2,500. And add this up, you have 2,850. So if you just compare these four scenarios, the best order quantity is the one with the minimal total annual cost, which is 500 pounds. Now, but in this case, we only picked four possible scenarios, and we computed the total cost for each scenario. But would you just look at only four possible scenarios and pick whichever produces the best results? No, there are other options, right? The order quantity can take any value. So what we can do is we can try all the possible values for the order quantity, and we can compute the total annual cost for each of these values, and we can choose the one that produces the lowest annual cost. And we can call it the optimal order quantity. The good news is that we already have a formula for the optimal order quantity. The optimal order quantity is the order quantity with the minimum total cost, which is the sum of the three types of costs. And it's given by the following formula. The square root of 2 times the ordering cost times the annual demand divided by the holding cost per unit per year. And this quantity is called the economic order quantity value, the EOQ value. Now, I want to make a few observations. I want to find the relationship between the order quantity and the annual inventory holding cost. As the order quantity increases, what happens to the annual inventory holding cost? So let's go back to the table. As the order quantity increases from here to here, the annual inventory holding cost is also increasing. Because remember, the formula for the annual inventory holding cost was Q over 2 times H. So as Q increases, this quantity will increase. So the annual inventory holding cost also increases. Now, what happens what happens to the annual ordering cost when the order quantity increases? When the order quantity increases, the ordering cost per year is decreasing. Why? Because as the order quantity increases, we will place an order less frequently, right? So we pay less money for the ordering cost. So as the order quantity increases, the ordering cost decreases. Now, how about the annual purchase cost? Let's look at the formula for the annual purchase cost. The annual purchase cost was D times U. So D is a fixed quantity, that's the annual demand, and U is also a fixed quantity. This is a unit cost. So this quantity doesn't depend on the order quantity. So if you look at this table, it's fixed. It doesn't change as we change the order quantity. So we can say that the purchase cost doesn't depend on the order quantity. It's a constant. So it's the same for all the order quantities. So what can we learn from this? We want to find the optimal order quantity that minimizes the total annual cost, which is the sum of these three types of costs. And since the annual purchase cost does not depend on the order quantity, we can try to find the order quantity minimizing the rest. these two costs. We can just drop the annual purchase cost from the formula. It doesn't change the optimal order quantity. So if we look at this graph, the x-axis is the order quantity, Q. The y-axis is the cost. As Q increases, the ordering cost is decreasing, and this carrying cost is the holding cost, and the holding cost is increasing, and we want to add them up. This is the sum of the two costs, and we want to find the order quantity, minimizing the sum. And here is some facts about this. So the quantity that minimizes the total cost is called the optimal order quantity, which is the EOQ value. And here is some fact about the graph. The minimum of this curve occurs when the two curves intersect with each other. Okay, so at the optimal order quantity, the y value of this curve is the same as the y value of this curve. In other words, the holding cost at the optimal order quantity is the same as the ordering cost at the optimal order quantity. Now, I want to introduce one more concept, the reorder point. The reorder point is the inventory level at the instance one places an order. So let's take an example. If it takes your supplier 2 weeks to deliver the order, when should you place an order? Your inventory will change like this over time, and we're gonna run out of inventory at this point, and at this point, and at this point. And since it takes 2 weeks until your supplier delivers an order, what should you do? To receive your order at this point, you need to place an order 2 weeks before you run out, right? So you need to place an order at this point. And the reorder point means how much inventory do you have at this instance you place an order. So how much inventory do you have at this point? Since you run out in 2 weeks, you have 2 weeks supply. 2 weeks supply, that's your inventory level at this point, and this is the reorder point. So how can you find 2 weeks supply? If the weekly demand is 30 weeks, how much is 2 weeks supply? 30 units times 2, 60 units. That's the reorder point. Now, can you find the formula for the reorder point? Yes, if the order lead time is X number of days and the reorder point, then the reorder point is X days supply, right? So the reorder point is the daily demand times the lead time in the number of days. Let's try this example. If the daily demand of your product is 10 units and the order lead time is 3 days, what's your reorder point? So the daily demand is 10 units and the lead time is 3 days. That's 30 units. That's the reorder point. So far we talked about the EOQ model, and here are the assumptions of the EOQ model. Demand is known and constant throughout the year. Only 3 types of costs, the unit cost, the ordering cost, and the inventory holding costs are considered, and shortages are not allowed. And under this setting, we derived some formulas for several interesting quantities. D is the annual demand, Q order quantity, U unit cost, O ordering cost, H holding cost, and you can use these formulas to find these quantities. Let's try a couple of exercise problems. Patterson Electronics supplies microcomputer circuitry to a computer that incorporates microprocessors into refrigerators and other home appliances. One of the components has an annual demand of 250 units. So this is D, and it is constant throughout the year. The inventory holding cost is estimated to be $1 per unit per year. So this is H. And the ordering cost is $20 per year. This is O. Patterson has been ordering 50 units each time an order is placed. So this is the order quantity Q. Number A, compute the annual ordering cost. Okay. So annual ordering cost, what's the formula for the annual ordering cost? D over Q times O. D over Q times O. So let's plug in the quantities. D equals 250, Q equals 50, and O equals 20. That's equal to 100. Number B, compute the annual holding cost. The formula for the annual holding cost is Q over 2 times H. So let's plug it in. Q equals 50 times H. H is 1, so this is $25. Number C, compute the number of orders placed every year. What's the formula for the number of orders placed every year? Here it is. The number of orders per year is D over Q. D over Q. So let's plug them in to 50 over 50. That's 5 times a year. Let's go to D. Compute the time between 2 consecutive orders. So what's the formula for the time between 2 consecutive orders? It's Q over D, and the unit of this quantity is the year. Q over D, year. So Q is 50, D is 250 year. So that's going to be 0.2 year. Or if you want to convert this into months, you can multiply by 12 months. So that's going to be 2.4 months. Let's go to E, compute the average inventory level. What's the formula for the average inventory level? That's Q over 2. So Q is 50. 50 over 2 is 25. Let's go to F. Compute the reorder point if the supplier takes 8 days to deliver the order. Assume 365 days a year. So what's the formula for the reorder point? The daily demand times the lead time in days. So what's the daily demand? We know the annual demand, which is 250. How can you convert this into a daily demand? Divided by the number of days in a year, right? So that's the daily demand times the lead time in the number of days. So what's the lead time? 8 days, right? So 8 times this ratio, that's 5.5, 5.5. Okay. So now let's try another example. Sumco purchases pump housing from a factory and sells them to other manufacturers. The annual demand is constant at 1,000 units a year. Placing an order to the factory costs Sumco $10 each time an order is placed. The unit cost is $40 per unit, and the annual average inventory holding cost per unit per year is $10.5. So the annual demand, this is D, and this is O. And this is the unit cost, U, and this is H. Let's go to A, compute the optimal order quantity. So what's the formula for the optimal order quantity? Right here. So we take the square root of 2 times D times O over H. So it's the square root of 2 times 1,000 times O is $10 divided by H is 0.5. Then you get 200. Now let's go to B, compute the annual ordering cost when the optimal order quantity is used. So the rest of the parts are very similar to the previous example. You can just apply the formula for the annual ordering cost, which is annual ordering cost is this, D over Q times O, D over Q times O. And for the order quantity Q, you just need to use the optimal order quantity, 200 units that you calculated in part A. And this is everything we have for this part, and I'll see you next time.